Hi everyone. So today we're going to do a new little bit with lines, and that's going to be finding the distance between a given point and a given line. Okay, so let's just start off with some line that looks like this. Let's call that L, and we've got some points. Let's say over here, we call that P. Okay, so there's many different ways to get from P to the line. So we can go along this way to the line, we can go along this way to the line. But what we're interested in is the shortest distance between the point P and the line. Okay, so that's going to be this distance over here. And you can show this, but we're not going to do that here, that the shortest distance here is actually perpendicular to the line. Okay, so we've got this line L, we've got this point P. If we draw a perpendicular line in green over here between the point and the line, then that is going to be the shortest distance. Okay, that's what we're trying to find. Okay, so this is the shortest distance, let's say between P and L. Okay, so we want to try and work out how do we find this distance given these two things. Okay, so let's just draw another little picture here just to figure out what this little triangle is here. So we're going to be using this triangle here. We're going to use this triangle to figure out what that distance is there. Okay, because we know it's a right angle triangle from before. So we can use that fact to find the distance, okay, using a bit of Pythagoras and trig and so on. Okay, so we're going to simplify this. Let's just say the line goes along horizontally. Okay, that's L. We've got a point P over here. Okay, and we're trying to find this vertical distance. Okay, let's call that D. Okay, so we want to do this as general as possible. So we're going to use the idea of vectors because we know that vectors work in 2 dimensions, it works in 3 dimensions. We can extend it to any number of dimensions. Okay, so we're trying to introduce vectors into this picture to allow us to find out what this distance is. Okay, so I'm just going to redraw this triangle diagram because we know we can use trig to work things out if we have a right angle triangle. So let's say we've got this point here, Q, and we've got this distance here. That distance there is QP, okay, the distance from Q to P. Okay, but what we're interested in is D, okay, which is the opposite to this angle at Q. Okay, so we are interested in D, which is opposite theta. Okay, now since it's opposite theta, we know that we can use one of our trig ratios. Okay, if it's opposite, we know that that's going to involve sine. So sine of theta is going to be the opposite, D, over the hypotenuse, which is QP. So sine theta is going to be the opposite, D, over the hypotenuse, which is QP. Okay, a little bit of rearranging. We can write this as D is equal to QP sine theta. Okay, so if we know QP and we know the angle theta, then we can find this distance D. Okay, but how can we do that in terms of vectors? Now we know Q is any point along the line, P is some other point, so we can find the vector going from Q to P. So we can find this vector here. Okay, let's call that W. Is going to be the vector at P minus the vector at Q. Okay, that will give us the hypotenuse W. The length of that vector is going to be the distance QP. Okay, so what we want to do is now find a relationship between all of these things. Okay, so I'm not going to prove this property here. You're going to be doing that for homework. So let's just put this down as a little homework exercise. The magnitude of A cross B is equal to the magnitude of A, or the length of A, times the length of B sine theta. Okay, that's the same theta that we have between the vectors, like we did with the cross product. Okay, so we want to prove this. Yeah, I'm going to give you a little hint. Okay, so the hint is, remember from the dot product that A dot B, we can write this as A1 B1 plus A2 B2 plus A3 B3. Okay, if we have components 1, 2, and 3 for both of them. We can also write this as the length of A times the length of B cos theta. Remember, we used that with our work on projections. Okay, so you can use this hint to prove the following formula here for the length of A cross B. Okay, so that's going to be the homework, but we're just going to use this formula now. You can go prove it later. Okay, so we're going to use this here. Okay, so again, we're interested in this sine of theta here. So we can write the sine of theta using the cross product of the two vectors. So if we've got W going along there, and we've got another vector along here, okay, remember a vector along the line, we called that V. So W cross V, what is that going to be? W cross V. This is going to be the length of W, which is our QP. Okay, that's what we wanted here. This QP there, that's what we wanted. Times the length of V sine theta. Okay, or we can write this as the length of W, we said that was QP. QP times the length of V sine theta. Okay, so that's W cross V. Now the right-hand side is almost what we want. We want QP sine theta. We've got QP times the length of V times sine theta. So let's take that length of V over to the other side. So W cross V over the length of V is QP sine theta, which is what we wanted. That's the length of that dotted green line. That's D. Okay, so we can use this to find the length D. Okay, so let's just write this out a bit neater so we can see. Okay, so we've got L, we've got a point over here. Okay, so I'm going to write this differently, just as R naught. So we can write this line as R of T is R naught plus T times V. Okay, R naught is just a point along the line. Same thing here, Q was just a point along the line. Okay, so it doesn't matter what point we pick, as long as it's along the line. Okay, so I'm just picking R naught as my Q. Then we've got P over here. Our perpendicular distance D. And this length over here. Okay, so remember we called that length W. this vector here was v. Okay, that's the vector we use to move along the line. So the distance from P to L, oh, I should say the shortest distance, sorry. The shortest distance from P to L is equal to, okay, so if we go back up here, we've got the cross product of W and V. So W was the vector along the hypotenuse. So we can write that as P minus R naught. That's the vector W along the hypotenuse. We take the cross product with V, which is this vector here from the equation of the line. Okay, if we go back up here, and we need to divide by the length of this V vector here. Okay, so let's put that in blue. That's the vector that goes along the line. That's in blue here. R naught, that's any point along the line. So we just take that one there. And P, that is the given point that we're interested in. That's going to be here. Okay, so with those 3 bits of information, we can find the distance from P to the line. Okay, are there any questions about this? Okay, let's have a look at an example. Okay, so let's say R of t is given by 1, 2, 3 plus t times 1, 0, minus 1. Okay, so that's our line L. Okay, and P, let's say that is the point 2, 0, 1. Okay, so we've got our line R, we've got our point P. We want to find the shortest distance from P to L. Okay, so let's find all the vectors that we need. So first we need to find that hypotenuse vector, that W from the diagram. That's going to be P minus R naught. Okay, so the hypotenuse vector W, that's going to be the vector going to P minus the vector going to R naught. So that's going to be 2, 0, 1 minus R naught. That's this first vector in the expression for R, the 1, 2, 3. Okay, we can subtract these. 2 minus 1, that's 1. 0 minus 2, minus 2. 1 minus 3, that's minus 2. Okay, so we've got our hypotenuse vector. Okay, next we need to take the cross product of the hypotenuse vector with the V vector from the equation of the line. Okay, so W cross V. Okay, remember that was that determinant where that first row was that RJK. Okay, that's how we did the cross product. So W, that's 1 minus 2 minus 2. And V, that's the vector attached with the T. That's 1, 0, minus 1. Okay, now we need to do the cross product. So we start with R, and we're going to get 2 minus 0. That one. Minus J, we're going to get minus 1 plus 2. And plus K, we're going to get 0 plus 2. Okay, so we can neaten that up. So the first component is 2. The second component, so we've got minus 1 plus 2. Yeah, that's going to be 1, but then we got the minus in front there, so that's -1. And then 0 plus 2, that's just 2. Okay, so that gives us our cross product, the hypotenuse vector W cross the vector V. Okay, now if we go back here, we need the length of this vector, or the magnitude of that vector. So the magnitude of W cross V is equal to the square root, and then we take each component and we square it. So it's going to be 2 squared plus, we have -1 squared plus, and then we have another 2 squared. Okay, so that's going to be 2 squared, that's going to be 4 plus 1 plus 4. Okay, so 4 plus 4, that's 8, plus 1, that's 9, root 9, that gives us 3. Okay. Okay, so we've got the numerator. Now we just need to find the denominator, which is the length of the V vector. So we can do that next. The length of V, what's that going to be? V was 1, 0, -1. So we can write this as the length of 1 squared plus 0 squared plus, and then the last one was -1, but remember we're squaring that, plus -1 squared. Okay, so that's going to be the square root of 1 plus 0 plus 1, so that's root 2. Okay, and finally, we can take the quotients of the two. So therefore, the shortest distance equals, we can just write out that was W cross V over V, length of V, sorry. So that's going to be 3 over root 2. Okay. And you can rationalize the denominator if you want to, but you don't really need to do that. So you could multiply by root 2 over root 2, and that would be 3 root 2 over 4. If you want to do that, that's fine, but that's not necessary. Okay, so then this gives us our shortest distance between the point and the line. Okay, any questions about this example? Okay, so it's not too bad, just a few steps that you need to go through. Okay, so you need to find the hypotenuse vector, okay, by taking the point P minus R naught, that gives you your hypotenuse. You take the cross product with V, okay, that's your W cross V. You find the length of that cross product, you find the length of V, take the ratio, and then that's your distance. Okay, so not too much to do. Okay, let's have a look at another example. Okay, so let's say R of T is 1 minus 1, 1. Okay, that's our R naught plus T times 1, 2, minus 3. Okay, so that's our line, L. And we want to find the shortest distance from P, which let's say is 0, 1, 2. Okay, we've got that point P, we've got the line given by R. What's the shortest distance? Okay, so the first thing we need to do is find that hypotenuse vector W. So that's going to be P minus R naught. Okay, we've got P, which is 0, 1, 2. R naught, that's the first vector here. That's 1, 1, minus 1, 1. Okay, so that's going to be 0 minus 1, that's minus 1. 1 minus minus 1, so it's going to be 2. And 2 minus 1, that's going to be 1. Okay, so that's our hypotenuse vector. Now we need to take the cross product of our hypotenuse vector with the vector V. So W cross V. Again, that's our determinant, but with that R, J, and K in the first row. Okay, W, we just worked that out. That was -1, 2, 1. V, that's given at the top there. That's 1, 2, -3. Okay, let's do this for each component. So we have R, and that's going to be -6, -2. Minus J, because we need that minus on there. That's going to be 3, -1. And plus K, that's going to be -2 minus another 2. Okay, so we can write this as a tuple just to make things a bit easier. So -6 -2, that's going to be a -8. 3 -1, that's going to be 2, but we got the minus in front, so that's a -2. And -2 -2, that's going to be a -4. Okay, so that is our W cross V vector. Okay, now we need to find the length of this vector. So the length of W cross V, that's going to be the square root, and then we square each of the components. So we have -8 squared plus -2 squared plus, so that's a plus, -4 squared. Okay, so -8 squared, that's just 8 squared, so that's 64. 2 squared, or -2 squared, that's going to be 4. And 4 squared, or -4 squared, that's going to be 16. Okay, so 16 plus 4, that's going to be 20, plus 64, that's going to be 84. So we get ourselves root 84. Okay, you might be able to simplify that now, but let's just leave it like that until the end. Okay, so that's W cross V. Now remember, for that denominator, we needed the length of V as well. So the length of V, that's the square root of the V vector, that was this bit over here, 1, 2, -3. So we're going to have 1 squared, then it was 2, so plus 2 squared, plus, and then it was -3, so -3 squared. Okay, so 1 squared, that's 1, 2 squared, that's 4, 3 squared, that's going, or -3 squared, or 3 squared, that's going to be 9. Okay, so that's going to be 9 plus 1, that's 10, plus 4, 14, so root 14. Okay, so finally we can take the quotients, and then that will give us the shortest distance. So shortest distance is equal to W cross V, the length of W cross V, sorry, over the length of V. Okay, the length of W cross V, we worked that out, that was root 84. And length of V, that was root 14. Okay, I'm sure you can simplify that down some more, but you can just leave it like that. That's fine. Okay, so that's going to be our shortest distance from the point to the line. Okay, any questions on this example? Okay, so that's between a point and a line. Next, we're going to look at the distance between two lines. Okay, now we know that if the two lines are intersecting, then the shortest distance is going to be 0 because they're touching each other. If the two lines are parallel, then the distance between them is going to be constant because they run next to each other. So The interesting case is when we are dealing with two skew lines. Okay, so distance between two skew lines. Okay, so the other cases are pretty boring. Okay, so remember what skew lines are. We've got one line going like this. Let's call that L1. And then we've got another line that crosses L1, but they don't intersect. So the lines are above each other. So, or let's say L1 goes above L2. Okay, so L1 is some distance above L2. Okay, but they're at some angle like this. Okay, so these are skew lines. Okay, so we want to find the shortest distance between them. So maybe it's something like this. We've got a point here and a point here, and this vertical distance between them, D, that's going to be like the shortest distance between them. Okay. Okay, so I won't go through the whole derivation now. We can do that another time, but I just want to show you the formula so you can work out some problems. So the formula for them is, the formula for the distance, shortest distance between L1 and L2. Okay, that's the D that we mentioned there. D is equal to absolute value of B1 cross B2 dotted with A2 minus A1 all over the length of B1 cross B2. Okay, so what are these A's and B's all about? Okay, so the A's and B's relate to the two lines. So where, let's say R1 corresponding to L1 is given by A1 plus T times B1. Okay, so instead of R0 and V, I'm using A1 and B1 to go with the line L1. And for the other line, R2, let's say that's lambda, so we don't mix up the two parameters. That's going to be A2 plus, almost wrote a T, lambda times B2. Okay, so they're the same as your R0 and your V0 and your V from before, but now just written in terms of A and B so we can separate them. Okay, so this is the formula for the shortest distance between two lines. Okay, so you can think about how you can come up with this formula. So it's very similar to what we did before. If we go back here, okay, with this diagram, where you draw out a diagram, you figure out the triangle, and then you can use a bit of trig to work out the side that you want. Okay, so here you need to figure out how do you draw the triangle? What kind of trig do you need to find this distance D? Okay, you can think about that for now, but then we'll go over it properly next time. Okay, but I just wanted to show you the formula so that you can do a couple of examples as homework. Okay, so let's say we've got R1 of T. That's given by 1, 2, 1 plus T times 1 minus 1 and 1. And R2 of lambda, that's going to be 2 minus 1 plus lambda, just so that they're different, 2, 1, 2. Okay, and just as a little extra bit, first show that they are skew. Okay, so they have to be skewed to use this formula here, because that's what we're trying to work out. However, just as a little bit of extra work from what we did last time, show that they are skew first, and then find out what the distance is. Okay, so that's the 2 bits of homework for today. Okay, any questions about what we've done today? Okay, any questions about the homework? Okay, so tomorrow we will go over how we get this formula, and then we'll do a couple more examples. And then next week we will start with the equations of planes, and then we'll find distances between planes, distances between points and planes, lines and planes, and so on. So all the stuff that we've done with lines, we're going to now do with planes. Okay, so I'll see all of you tomorrow. And then I'll upload the homework a bit later today, and then you can check your answers. Yeah, bye everyone.